Okay, so here is the electricity and magnetism problem, the second one from the 2007 AP. So the problem is, well, the setup for the problem is that there's a central insulating solid sphere of radius A with charge plus Q uniformly distributed throughout its volume, concentric with a non-conducting spherical shell of inner radius 2a and outer radius 3a that has a charge negative Q uniformly distributed throughout its volume. And they want you to express all the answers in given quantities and fundamental constants. So part A is using Gauss's law to derive expressions for the magnitude of the electric field as a function of the radius r in the following regions. So the regions defined are 1, within this solid sphere in the middle, so r is less than a. You have 2, between the solid sphere and the spherical shell, where a is less than r is less than 2a. And then there's a third region where you're within the spherical shell, so r is greater than 2a and is less than 3a. And then you have the fourth region where it's outside of the spherical shell. So r is greater than 3a. Okay, so for part 1, where the radius is less than a, you start out with Gauss's law, as asked. So Q inside epsilon naught. So EA is equal to Q inside over epsilon naught. So A in this case is equal to 4 pi r squared. Q inside is equal to rho V. Rho is equal to the total charge over the volume, and these two V's are different. So this V right here is equal to 4/3 pi r cubed, and this V over here is equal to 4/3 pi a cubed, because this is the density of the inner sphere, and this is just the volume of the radius that we're looking at. So therefore Q inside is equal to Q over 4/3 pi a cubed times 4/3 pi r cubed. That cancels out to equal Q inside is equal to Q over Q over a cubed times r cubed. You plug that back into your Gauss's law equation, so A equals Q inside over epsilon naught. E times 4 pi r squared is equal to Q r cubed over a cubed epsilon naught. E is equal to 1 over 4 pi epsilon naught r squared times r cubed over a cubed. E is equal to k r over a cubed. And there you have part 1. So part 2 now, I'm just going to go to the side here, deals with the area between A and 2A. And for part 2, the charge is here, and the distance or the radius is going to be in this region right here. Because of that, you can treat this middle part as a point mass, or just Q as normal. So EA is equal to Q over epsilon naught. E times 4 pi r squared is equal to Q over epsilon naught. E is equal to 1 over 4 pi epsilon naught times Q over r squared, and E equals K Q over r squared. That is pretty straightforward. Okay, so starting on a new sheet of paper, part 3 is the electric field when you are in between when you are inside the spherical shell outside. So again, you start with EA is equal to Q inside over epsilon naught. But in this case, while A is the same, Q is different. So Q, you have to sum the middle part, the positive part, and the negative part that is inside. So you start like usual, Q inside is equal to Q. And then now you have to say minus rho V for the parts inside, for the parts of the shell. So rho is going to be equal to, and because I already put the negative sign there, rho is going to be equal to Q over V, and this V is equal to 4/3 pi 3a cubed minus 4/3 pi 2a cubed. And that's because the only volume that you're summing for the negative charge is the part over here. You're not summing the inside part, which is the radius 2a. This V up here is the part that is inside R, so you do 4/3 pi R cubed minus 4/3 pi 2a cubed. So this gives Q inside is equal to Q minus Q over V Q over V times another V, and then this gives Q over 4/3 27a cubed minus 4/3 8a cubed times 4/3 and that's all multiplied by pi. 4/3 pi R cubed minus 4/3 pi 2a cubed. And that simplifies out to Q minus Q over 19 a cubed times R cubed minus 8a cubed for Q inside. So now you go back into Gauss's law way up here, plug it in. EA is equal to Q minus Q over 19a cubed times R cubed minus 8a cubed, and I should have put parentheses around these terms, over epsilon naught. E and A is still equal to 4 pi R squared for a Gaussian surface, equal to above, and then you go and divide both sides by 4 pi R squared. So E is equal to 1 over 4 pi epsilon naught times, and this is getting quite hairy, minus Q over 19 a cubed times R cubed minus 8a cubed, in parentheses, all over R squared. And that is an acceptable answer. I really don't know how to simplify that any more than I have. So that is part 3. Part 4 again becomes much more simple, much simpler. So now the net charge outside for EA equals Q inside over epsilon naught. Q inside is now equal to 0 because the net charge is 0 from when you add these two charges and you're outside of the spherical shell. So you plug it in, E is equal to 0. So that is part A of this question. Part B of this question is asking for the electric potential at the outer surface of the spherical shell where R is equal to 3A. So again, we have our big shell. You have this, and and they're asking for the potential at this distance right on the surface. So the electric potential here will be equal to E times D E or KQ over R. Either way, in this case, the charge or the electric field is equal to 0. So V will equal to 0. There will be no electric potential at this point. Part C of this question is asking for the electric potential difference between the point labeled Vx, and x is right here, and y right here. So the potential difference between the radius at 2a and the radius at a. So electric potential is equal to kq over r for spherical shells, for spherical objects or point masses. In this case, Vx is equal to k times q, because it's only affected by stuff inside of it, over r, and r is 2a. Vy is equal to kq over a, and the question is asking for the electric potential difference of Vx minus Vy. That gives us kq over 2a minus kq over a, which simplifies to minus 1/2 kq over a.